Hello my dear students, welcome to chemistry session. This is Tagoor, your chemistry lecturer. In previous class, we discussed about introduction of p block elements and physical properties of boron family. In this video, we discuss chemical properties of boron family. Chemical properties of boron family. The first reaction or first chemical property is reaction with air. Reaction with air. Reaction with air. Boron and aluminium in crystalline form. Boron and aluminium in crystalline form. They are not reactive. They are not reactive. In crystalline form, they are not reactive, but in amorphous form, they can react with air to form corresponding oxides and nitrides. Form corresponding oxides and nitrides. To form corresponding oxides and nitrides. The general oxidation state of boron family is +3. The general oxidation state of boron family is +3. The general oxidation state of oxygen is -2. So they can forming M2O3 so they can forming M2O3 type oxides. They can forming M2O3 type oxides. The general oxidation of group 13 is +3. The charge present on nitrogen is -3 and -3. So they can forming Mn type nitrates. The general oxidation state of boron family is +3 and nitrogen having charge -3. So they can forming Mn type nitrides. Mn type nitrides. Mn type nitrides. Elements of group 13 elements reacts with nitrogen to form corresponding nitrides. Elements of boron family reacts with oxygen to form corresponding oxides. Corresponding oxide. But aluminium is not react completely. Aluminium is not completely react with oxygen because formation of protective oxide layer on surface of the aluminium metal. Due to the formation of protective layer on surface of aluminium metal, this completely not completely reaction with oxygen. Boron oxide. Boron oxide on hydrolysis it gives boric acid. On hydrolysis of boron oxide it gives boric acid. Boric acid. Boric acid or orthoboric acid is one of the important compound of boron. It is one of the important compound of boron. The hybridization of boron in boric acid is sp2 hybridization. sp2 hybridization. What is the hybridization of boron in boric acid or orthoboric acid? Hybridization is sp2 hybridization. Boric acid having structure like this. The plane of AO3 units are joined by hydrogen bonds. Next, the nature of oxides of boron family. The nature of oxides. B2O3 oxide is a acidic nature. Boron is being a non-metal. Boron is a typical non-metal. So oxides of boron are acidic in nature. acidic in nature. Next, aluminium and gallium. Aluminium and gallium are amphoteric in nature, so their oxides are amphoteric in nature. Amphoteric means they can exhibit acidic nature as well as basic nature. Next, indium oxides and thallium oxides are basic in nature. Basic in nature. This is the nature of oxides of boron family. Nature of oxides of boron family is important. Boron oxides are acidic in nature. Aluminium and gallium oxides are amphoteric in nature. Indium and thallium oxides are basic in nature. The reactivity of boron family towards oxygen increases down the group. Down the group, the reactivity of boron family towards oxygen increases. Towards oxygen increases. Reaction with water. Second property is reaction with water. Reaction with water. Under ordinary condition, boron is not affected by water. Under ordinary condition or normal condition, boron is not affected by water. But when steam is passed over red hot boron, it liberates hydrogen gas. It liberates hydrogen gas. But when steam is passed over red hot boron, hydrogen gas is liberated. Hydrogen gas is liberated along with boron oxide B2O3. Boron reacts with water at red hot condition. It gives boron oxide or boric anhydride along with hydrogen gas liberation. Similar reaction is also observed in case of aluminium. Aluminium reacts with water to form aluminium oxide and hydrogen gas. Hydrogen gas. Aluminium decomposes cold water. Aluminium can decompose cold water if protective oxide layer is not present on surface of the metal. If this protective oxide layer is not present on metal surface, aluminum can decompose the cold water. Aluminum decomposes cold water if oxide layer is not present on its surface. On its surface, only aluminum reacts. Only aluminum reacts with boiling water. Only aluminum can react with boiling water. Thallium can form in thallium hydroxide in moist air. Unless oxygen is present, thallium can form thallium hydroxide in moist air. Thallium reacts with water, grades of oxygen to form thallium hydroxide. It is the balanced chemical equation of formation of thallium hydroxide. Thallium hydroxide. Next, gallium and indium. Gallium and indium does not react with water. React with water. Does not react with water. Gallium and indium are not react with water. Third property or third reaction is acids and alkalis. Reaction with acids and bases. Third reaction is reaction with acids and bases. Bases are alkalis. First, action of acids. First we discuss action of acid. Boron does not react with non-oxidizing acids such as HCl. Boron is not reacting with non-oxidizing acids. Non-oxidizing acid such as HCl. HCl is a non-oxidizing acid because it does not having oxygens. HCl is not having oxygens. So it is a non-oxidizing acid. At high temperature, boron reacts with strong oxidizing acids. At high temperature, boron reacts with strong oxidizing acids such as concentrated sulfuric acid and concentrated nitric acid mixture to liberate NO2 gas. To liberate NO2 gas. Boron reacts with concentrated nitric acid in presence of sulfuric acid to liberate NO2 gas. NO2 gas. It is important reaction of the boron family. This reaction is one of the important reaction in boron family. Boron reacts with concentrated HNO3, that means nitric acid in presence of sulfuric acid. It liberates NO2 gas along with boric acid H3BO3. The ratio of acid is, this is 2, this one 1:1 ratio. Concentrated H2SO4 2 moles, HNO3 is 1 mole. All other elements react with both oxidizing and non-oxidizing acids. Boron is not react with non-oxidizing acids, but all other elements can react with both oxidizing as well as non-oxidizing acids. Non-oxidizing acids. Aluminum reacts with non-oxidizing acid like HCl, it forming aluminum chloride AlCl3. AlCl3. Aluminum reacts with non-oxidizing acid HCl, it gives aluminum chloride along with hydrogen gas. Aluminum reacts with oxidizing acid, that is nitric acid, liberate NO2 gas, aluminum oxide and water. Aluminum reacts with HNO3, it is a oxidizing acid, it gives aluminum oxide, NO2 gas and water. Next, action of alkalis. Next, action of alkalis or bases. Action of alkalis or bases. Boron resists. Boron resists towards alkalis. Towards alkalis up to 773 Kelvin temperature. Boron is not reactive towards bases up to 773 Kelvin temperature. But above 773 Kelvin temperature, boron reacts with bases to form borates and hydrogen gases. Hydrogen gases. Boron reacts with potassium hydroxide base at above 773 Kelvin temperature. It gives potassium borate. Potassium borate and hydrogen gas. Similar reaction is also observed in case of NaOH. If boron reacts with NaOH, 6 moles of NaOH, 6 moles of NaOH, we get 2Na3BO3, 2Na3BO3. Sodium borate. Sodium borate. It is sodium borate. Sodium borate. Sodium borate. Boron reacts with base, that is sodium hydroxide. It gives sodium borate and hydrogen gas. 3H2. 3H2. Aluminum reacts with sodium hydroxide base in presence of water. It gives complex and hydrogen gas. Sodium tetrahydroxy aluminate eliminate 3. Eliminate 3. Aluminium reacts with aqueous sodium hydroxide. It gives complex is sodium tetrahydroxide. Eliminate 3. 2Na plus AlOH taken by 4 minus. Similar reaction is also observed in case of gallium. Gallium reacts with sodium hydroxide. It gives complex sodium tetrahydroxide. Gallium 3. Next, indium and thallium. Indium and thallium are not react with bases. Indium and thallium are not reactive with alkalis. Indium and thallium do not react with alkalis. Fourth property, action of halogens. Fourth chemical property of boron family is reaction with halogens. Reaction with halogens. Boron family elements can react with halogens. They can forming trihalides except TlI3. The general oxidation state of group 13 elements is +3. Halogen having minus, so they can forming MX3 trihalides. Boron family elements can react with halogens. They can forming trihalides. For example, boron reacts with chlorine Cl2. It gives boron trichloride BCl3. For the balancing reaction, 2B 2 3s are 6, 3Cl2. Elements of group 13 elements reacts with halogen to form trihalides. These trihalides are electron deficient molecules. For example, BCl having 6 electrons. Here 2 electrons. This bonding having 2 electrons. This bonding having 2 electrons. Total electrons 6 electrons. So it is electron deficient molecule. The hybridization of boron here sp2 hybridization with trigonal planar shape. The trihalides formed by boron family are trigonal planar shape with sp2 hybridization. Here exception is thallium. Thallium is not forming TlI3 is not exist. Thallic chloride TlCl3 is decomposed to TlCl to give Cl2 gas. In TlCl3, thallium having +3 oxidation state. In TlCl, thallium having +1 oxidation state. In thallium is highly unstable at +3 oxidation state. Thallium is highly unstable at +3 oxidation state due to inert pair effect. So it readily undergoes reduction to give TlCl +3 to +1. So it undergoing decreasing in oxidation number. It is called reduction. Decreasing in oxidation number. So it is called reduction. So TlCl3 is a good oxidizing agent. TlCl3 is a good oxidizing agent. It is readily decomposed to TlCl and Cl2. Here chlorine having -1 oxidation state and here having 0 oxidation number. So chlorine undergoing oxidation, undergoing oxidation, undergoing oxidation. Chlorine TLCl3 having -1 oxidation state, here having 0 oxidation number. The increasing oxidation number is called oxidation. Increasing of oxidation number is called oxidation. Decreasing of oxidation number is called reduction. So in chlorine is undergoing oxidation, so it acts as reducing agent. In TLCl3, thallium acting as oxidizing agent. Cl ion is acting reducing agent. Due to oxidizing character of TL3 coupled with reducing character of Cl- and Br-. Due to oxidizing character of TL3 ion, it is combined with reducing character of Cl- and Br-. Here also same, +3 oxidation state and +1 oxidation state. Next, TLI3 does not exist. TL3 does not exist because oxidizing character of TLI3 and strong reducing character of I- ion. Strong reducing character of iodine ion. Due to oxidizing character of TLI3 ion, strong reducing character of I- ion, TLI3 is not exist. TLI3 is not exist. Important one. TLI3 is not exist. Boron reacts with chlorine to form boron trichlorides. Aluminium reacts with chlorine to form aluminium chlorides. Here representation of boron is sp2. Shape of boron trichloride is trigonal planar. These trihalides are electron deficient compounds, so they can act as Lewis acids. Trihalides are electron deficient molecules, so they can act as Lewis acids. Electron deficient compounds can act as Lewis acid by accepting a pair of electrons. For example, BF3 is an electron deficient compound. It reacts with ammonia NH3 having electron lone pair of electrons to form complex NH3 BF3 complex. Similar reaction is also observed in case of BCl3 reacts with ammonia, it forming complex NH3 BCl3 complex. It is a Lewis acid. BCl3 is a Lewis acid. Ammonia is Lewis base. Trihalides are electron deficient molecules, so they can act as Lewis acids. They can react with Lewis bases to form complexes, and they complete the octet configuration. It is the order of Lewis acid character. There is increasing order of Lewis acid character. Or strength of the Lewis acid. It is increasing order of Lewis acid character or strength of the Lewis acid. Here BF3 having least Lewis acid character when comparing with remaining trihalides of boron. Because in BF3 back bonding is present. back bonding is present. BF3, this is BF3 structure. This BF3 structure. Boron having one empty orbital. Boron having one empty orbital. Electronic configuration of boron 1s2, 2s2, 2p1. 1s2, 2s2, 2p1. 2p1 means 2px1 in excited state. 2s1, 2px1, 2py1, 2pz0. Excited state 1s orbital, 2p orbitals undergoes to form sp2, 3 sp2 hybrid orbitals. In excited state, boron undergoing intermixing of 1s orbital, 2p orbitals to produce 3 sp2 hybrid orbitals. It having 1p empty orbitals. Is p empty orbitals. Empty or vacant orbital. Empty orbitals. These empty orbitals, boron here. Boron having empty orbitals. Fluorine having 3 lone pair of electrons. Each fluorine having 3 lone pair of electrons. Each fluorine having 3 lone pair of electrons. So, one lone pair of electron is donated to empty orbital of boron. Here p-pi back bonding is formed. P-pi back bonding. P-pi back bonding is formed. Due to small size of boron and fluorine. Due to p-pi back bonding is formed between empty p orbital of boron and filled p orbital of fluorine. Filled p orbital of fluorine. So bond order here 1.33. 1.33. Bond order is 1.33. In BF3, bond order is 1.33 due to back bonding. Fluorine. Denoting is forming back bonding. Similarly, fluorine. Similarly, this fluorine also can forming back bonding. This fluorine also can forming back bonding. Due to presence of back bonding, BF3 having bond order 1.33. Here bond order is 1.3. Important. Bond order is 1.33. In BF3, bond order is 1.33, not 1. These are called no bond resonance. These are called no bond resonance structures. No bond resonance structures. This is the Lewis acid character order. Next, if you are comparing bond length of BF3 and BF4 minus. BF3 and BF4 minus bond length. BF4 having more bond length. BF bond length. Here we are comparing BF bond length. BF4 minus having more bond length because in BF3 back bonding is present. Back bonding is present in BF3. But in case of BF4 minus, no back bonding. No back bonding. No back bond because in BF4 minus structure, fluorine. It completing its octet. Boron here having 2 plus 2 plus 2 plus 2. 4 2s are 8 electrons. It completes its octet. Here bond order is 1. Here bond order is 1. Bond order is 1. But in case of BF3, bond order is 1.33. 1.33. 1.33. In BF3 bond order is 1.33. In BF4 minus bond order is 1. So if bond order increases, bond length decreases, bond stability increases. If bond order increases, bond length decreases, bond stability increases. So BF3 having more bond order than BF4 minus. So BF bond length is more in BF4 minus. Similarly, boron hydroxide is more bond length than boron OH, taken rise 4 minus. B boron hydroxide, boron tetrahydroxide is having more bond length. Due to the presence of here back bonding is present, here back bonding is not present. This is the reaction of halogens with boron family. Next, anomalous behavior of boron. Anomalous behavior of boron. In periodic table, in every group, first element can differ with rest of the elements. In periodic table, in every group, first element of each group can differ with other elements in chemical properties. It is due to the reasons. Boron, anomalous behavior of boron reasons, absence of d orbitals. Due to absence of d orbitals, very small atomic size, that is 88 picometers, very high electronegativity of boron, that is 2.0, and very high ionization enthalpy. Anomalous behavior of boron is due to absence of d orbitals, very small atomic size, very high electronegativity, and very high ionization enthalpy. Due to these following reasons, boron can differ from rest of the elements. Boron can show different properties with other elements. These are the points difference. These are the points difference between boron and rest of the elements. Boron is a hard metal, while other elements are soft white metals. This is the crystalline form of boron. In black color, hard non-metal. Remaining rest of the metals are white in color. Aluminium, gallium, indium, and thallium. First difference is boron is a hard black non-metal, but remaining elements are white soft metals. Boron can show allotropy. But remaining elements cannot show allotropy. Boron can show allotropic property, but remaining elements of group 13 do not show allotropy. These are the two forms, allotropes of the boron: crystalline form and this is amorphous form. This one is crystalline form of boron. Third difference is amongst elements of group 13. Elements, boron is having highest melting and boiling point. Than rest of the group elements. Boron is having highest melting and boiling point because it having B12 icosahedron units. Due to presence of this polymeric structure, boron is having highest melting and boiling point. And boron is also having most stable hydrate. Boron is also forming most stable hydrate. Boron is not affected by non-oxidizing acids. Boron is not affected by non-oxidizing acids, but remaining elements can react with non-oxidizing acids. Boron forms only covalent compounds. Boron forms only covalent compounds due to extremely small size. Boron is formed due to extremely small size. They can forming only covalent compounds. Boron is formed only covalent compounds due to small size, but remaining elements can forming covalent compounds as well as ionic compounds. But remaining elements can forming ionic compounds and covalent compounds. Only boron combines with active metals. Only boron combines with active metals. Remaining elements are not combines with active metals. Boron can combine with active metals, it forming metal boride, metal borides. For example, boron reacts with magnesium active metal, it forming magnesium boride, magnesium borides, it forming borides. Seventh property, boron does not decompose. Boron does not decompose water or steam at room temperature. Boron is not decompose water at room temperature. For example, boron plus water at 25 degrees centigrade, no reaction. Boron reacts with water at room temperature, reaction is not possible. Next property is boron dissolves in concentrated HNO3. Boron can dissolve in concentrated HNO3, but remaining elements are passive with concentrated HNO3, especially aluminium and gallium. Boron is dissolves in concentrated HNO3 to form boric acid. But other elements are passive, especially aluminium and gallium. Boron reacts with concentrated sulfuric acid HNO3 in presence of H2SO4. It gives boric acid along with NO2 gas liberation. It is important reaction. Boron reacts with HNO3 in presence of H2SO4, it giving boric acid and NO2 gas. Boron halides due to the absence of d orbitals. Boron halides due to the absence of d orbitals, they can forming tetrahedral complexes. Tetrahedral complexes, but remaining elements can forming octahedral complexes. Octahedral complex due to the presence of d orbitals. Boron halides are on heterosis. They can forming tetrahedral complex because absence of d orbitals, but rest of the elements can forming octahedral complex due to the presence of d orbitals. For example, BH3, BCl3, boron halide, trihalide reacts with water H2O. It forming boron tetrahydroxide minus due to absence of d orbitals, but remaining can forming octahedral complexes. Here hybridization of boron is sp3. Here hybridization of aluminium is sp3d2. sp3d2. Hybridization of boron tetrahedral complex is sp3. In aluminium complex, aluminium hybridization is sp3 to hybridization. Boron having covalency 4, but remaining elements are having 6. Boron can exhibit maximum covalency 4, but remaining elements can exhibit maximum covalency 6. Maximum discuss about the diagonal relationship of boron with silicon. Diagonal relationship of boron with silicon. Boron can shows diagonal relationship with silicon because due to similar electronegativity values and same polarizing power. Due to similar electronegativity values and same polarizing power of V plus 3 ion, due to same polarizing power of V plus 3 ion and Si plus 4, they can show in diagonal relationship. Both boron and silicon forms weak acids. Both boron and silicon can form weak acids H3BO3 and H2SiO3. Both boron and silicon halides are readily hydrolyzed. Both silicon and boron halides are undergoing hydrolysis to give boric acid. In case of boron, salicylic acid in case of silicon. Boron trichloride undergoing hydrolysis, it gives boric acid. Silicon tetrachloride undergoing hydrolysis, it gives salicylic acid along with hydrochloric acid. Both elements react with metal from borides. Both elements can react with metals to form borides. Boron reacts with magnesium metal to form boride. Similarly, silicon is also reacts with magnesium to form borides. Both the elements can react with active metals forming borides. These carbides of these elements are very hard. The carbides of these elements are very hard. So they can use it as abrasive. Okay, this is the class for today.